When a user interacts with a virtual agent through mixed reality devices, it is necessary to consider the semantics of the scene in the real world to position the virtual agent. It may help to avoid unnatural interaction experiences, like a virtual agent floating in the air when being interacted with. In this paper, we propose a novel approach to use the scene semantics to guide the positioning of a virtual agent. Due to the characteristic of mixed reality, blending of the real world and digital world, it may cause inconvenience and unnaturalness to the user, if a mixed reality system does not consider the semantics of a scene. Some applications place the virtual agent directly in front of a user, causing the virtual agent to float in the air, like Pokémon Go. An alternative, commonly applied method is to set some surfaces on objects and place the virtual agent on these surfaces. Without considering the scene semantics, the interaction experience can also be influenced. For example, the virtual agent includes some key objects what the user is watching, like computer or books on the desk. Our approach contains two parts, pre-processing and optimization. In the pre-processing part, our approach reconstructs the 3D scene and implements the detection to obtain the semantics of the scene, including what and where the objects are. In the optimization part, our approach optimizes the location and orientation of the virtual agent iteratively. A cost function with a visibility term and a spatial term is designed to model how well the location and orientation of the virtual agent is. The visibility term ensures the user's view of watching key objects would not be occluded by the virtual agent. The spatial term controls the distance and orientation to fit a normal user's conventional choice. An optimization algorithm is applied to search for an appropriate position. We design three types of interaction tasks which cover the common interactions between users and virtual agents. They are communication task, teaching task and guiding task. Optimized by our spatial cost, the virtual agent sits on a chair and communicates with the user, maintaining a certain social safety distance with a reasonable orientation. In the teaching task, the virtual agent stands nearby the oven and teaches the user to cook. Since the virtual agent needs to teach the user to cook step by step, it cannot block the key objects, the vegetables, in this interaction task. Our visibility cost can constrain its occlusion during the optimization. In this guiding task, the virtual agent is introducing the food in the refrigerator to the user. Under the limitation of visibility cost, the virtual agent does not have too much occlusion of the key object, the refrigerator, drinks or fruits in it, so that the user can see the food. Our approach can also be used in other scenes like introducing the goods nearby a vending machine, displaying a propped box to provide user with information about work in a classroom, guiding the user to find books in a library, or interacting in a meeting room. In order to evaluate the results of our approach, we design a user study to compare the positions optimized by our approach with two methods mentioned in the motivation. Each participant needs to give a location score, an orientation score and an overall score for each result, ranging from 1 to 5. Through statistical analysis, we can conclude that the positioning approach based on scene semantics is more effective than the other two methods. Specifically, the average score in the user study was higher, and the standard deviation was smaller. The results of ANOVA test also showed that the effect was significantly different from the other two. We packaged our approach as a plugin which runs in Unity. Here how it works. The user loads a pre-processed scene model and the scene semantics information. The position of the user will transmit to the plugin via Wi-Fi. When we click User Setting button, a human-like model will be loaded. After that, we can click Start button to begin the optimization. We provide cameras from different views and show the cost values in real time. Finally, we can obtain an optimized position for the virtual agent which is appropriate when interacting. Our work introduces an approach for virtual agent positioning based on scene semantics via mixed reality, which can more effectively locate a virtual agent at a suitable place, compared to traditional approaches. Imagine that when you enter a new apartment, the virtual agent greets you, directs you around the room, and introduces you to the surrounding environment. How convenient the interaction is! This is the end of our video. Thanks for watching.